This is video 43 on MicroPython and LVGL 9. The binding approach introduced in video 35 provides a different set of MicroPython modules to configure LVGL displays. In this video, we utilize the LCD bus to configure 16 parallel data lines to the ST7262 display that is 800 by 480 pixels. Please let us know in the comments if you like this example, or let us know if you have suggestions to improve it. For this effort, our test rig uses a Waveshare ESP32-S3 MCU integrated with a 4.3-inch display, a capacitive touch panel, and a TF card adapter. As this channel covers multiple small system solutions over time, please subscribe to stay informed, and click like, as that really helps. Our goal is to use the LCD bus modules to configure the Waveshare device. We will demonstrate a working program, explore the Waveshare wiki to understand the components, discuss the LCD bus modules used to configure the Waveshare components, review the display and SD card drivers. The firmware and code files are at the GitHub site that is mentioned in the description and endnotes for this video. Our example is the test matrix LCD bus. I have the program running in the display. Let's press a few buttons on the display. You can see that as I touch various areas on the panel, that the screen responds very quickly and easily to each of the coordinates on the matrix display. This program demonstrates the size of the display and the ease of using a capacitive touch panel. Later, we will demonstrate another example using the SD card interface. From an internet search, we can see pictures of the many features of the display. Here, I summarize the components of interest to us. Please notice that the display uses 16 parallel data lines, which means we cannot use the simple SPI serial interface. Likewise, the touch panel does not use SPI to XPT 2046. Instead, the touch panel uses an I2C interface to a GT911 device. All of these data lines are not available on the ESP32 chip, so Waveshare included an I/O expander. Finally, it's nice to see they used a standard SPI interface to the TF card. The Waveshare website directs us to a wiki site to get information in Arduino file downloads. Fortunately for us, they include a schematics file that summarizes the pinout and wiring of the various components. This helps us make good decisions on coding the components. We have two firmware available for the ESP32-S3 chip. We chose the firmware that contains Schlosser's new binding approach modules that are used in video 35. This firmware contains modules that support the LCD bus, in other words, the RGB interface. Regarding displays, RGB is a term applied to a parallel 8 or more data line interface, as opposed to a serial interface of SPI or I2C. Because we need an RGB interface, we need MicroPython modules to be configured differently than previous videos. Fortunately, a lengthy LVGL forum discussion between Kevin Schlosser and Gitzner H provides us with the coding approach. The next 5 slides outline the configuration. Although I walk through them quickly, we will also do a detailed code review a bit later. We begin with the display. Schlosser's LCD bus includes an RGB bus setup. Included in the RGB bus setup is a set of H-sync and V-sync values that replace a typical display driver's initialization step. Notice that the frame buffers utilize the SPI RAM memory. Finally, we have to include the task handler, which has been hidden in past LVGL 9 programs. The firmware includes the GT911 touch driver, which makes use of the I2C bus and device functions. Gitzner provides the CH422G driver and configuration. The SD card interface utilizes a SPI bus as described by the schematics. Finally, we can use the standard LVGL file system functions. At the bottom of the screen, I show a specific font is loaded by reading the SD card file. The result is that we have 3 new driver files to contain the above functions, and we load the font files in a directory on a TF card. Now, let's walk through the 2 driver files. Okay, I've turned off the display. Let's look at just the Thony so we can understand the code. Well, let's begin with the display driver. In the display driver, we see the important files. So there's an LCD bus, there's an RGB display, there's a task handler. Here we bring in I2C, the GT911, and of course our reset in case we need to restart the system. So all of these imports need to occur. Next, we configure the RGB bus. What you can see is the pinouts from the schematics. Only Schlosser was the one to point out that it needs to be in a certain order. This display is got the RGB differently. It's got BGR. And so we need to have our colors in that same sequence. Here's the H-sync and V-sync parameters that I talked about. That concludes the LCD bus. Next, we define 2 buffers. These buffers can be small, hence they're just width times the height times 2. Next is the RGB display. The RGB display takes into account the width and height, the buffers, the backlit pin, which is number 2, and the color format. And this display works in RGB 565. Next, you'll see that we've initialized the display, which is something that is different from our other interfaces. And note that I mentioned that the display defaults to landscape mode. Also, I found that the backlight is already turned on, and that's probably because of this backlight pin definition up above. Another item to note is the task handler is defined at this point. You must have this in there or the screen will not work. Finally, we come to our InDev. And here you see the commands to set up the GT911. Let me move this out just a little bit. It's using an I2C bus, which is defined as so. And we're using the host, the I2C 0, which is host equals 0. So that's what that means. And then these are pins 9 and 8, which are the I2C 0 pins. Next, we utilize the GT911 driver, which is already on our firmware. And it has the address, and it has some configuration bits. Finally, we define the InDev using this GT911 driver. Notice its startup rotation is 0. Finally, Schlosser has us do these special configurations on the InDev hardware size using the width and height. Notice that on line 82, we initialize the touch. So this is just defining what the touch is going to be, and then we execute it. All right, there's the display driver. A lot of changes. Let's take a look at the SD card now. Okay, I brought in the SD card driver, and this is just to hold all the definitions for the I/O expander and the CH422G. This is to hold all the The SD card driver holds all the definitions for the I2C interface as well as the I/O expander, as you'll see. So as you recall from the display, we're using I2C 0, and we continue to do that here in the definition of the I2C bus for the I/O expander. So it's on the same bus as the touch. And the I/O expander is there to provide additional pins to the program because all of the pins have been consumed by the 16-bit 16 data line interface to the display. So we need a few extra pins in order to set certain functions on the display and the touch and the SD card. And so they're important in order to drive and control the devices, but not as important as the data lines. So we can use this I/O expander, basically to just turn pins on and off. And so the example from Schlosser and Gitzner H that I saw, he had these pins all defined, although you'll see that we're not going to use these for the SD card. Just this pin right here on line 54 is used for the SD card. From the schematic, we found that EXI04 pin on the I/O expander is used to set the chip select for the SD card. And so you see here, he sets his pin out as we would normally do. He sets the default to 0 because a few seconds later, he's going to turn it on. And his comment in German here is saying that this CS, in other words, the chip select pin, must be high in order for the SD card to work. And I think that is what allows us to do what you're going to see in a few seconds. All right, next he defines the SPI bus, which is using SPI2, using the standard pins that we've seen before. And he uses a feature of the machine module, which is SD card. And here he has the chip select as 2. Now, if you recall, the chip select 2 is the backlight pin that we used above. And that's because I must have something here. I can't put -1 or none. The commands don't like that. So I put in 2, which doesn't hurt anything because it's already set high in order to turn on the backlight. And we need it high in order to chip select the SD card. So no problem here. And this is the frequency that they used in one of the examples I saw in the LVGL forum. And finally, I include some commands when I was first setting this up, but you'll see these later in our program. Now I have an example program that I used to test the SD card, and I'm going to turn the display back on. Okay, I've started the test_button2_LCD bus program, and you'll see that it's displaying a single button in the center of the screen with the text 1. So let's run the program. And you see that when I touch the button, it reports in the shell that I've touched it. And if I touch it again, it reports click button 2. All right, what we're going to focus on is the font of that text 1. So in the program, past the setup, so there's the import for the SD card driver, which we've imported as the SD device. Then we mount the SD device as the /SD. We change our directory to /sd. And then we bring in the FS driver definitions. And finally, in our program, we have the definition for the font. So here I'm showing the definition for Montserrat Med 28, and we're using the LV bin font create. And this function only works if it's reading from a file system. So you can see here it's using the FS driver's S drive to read the font directory, and we're reading the Montserrat 2018, 28, and 36 of Alex Brush. So later on, down in the screen, you'll see where I've defined the program to use this particular font. So we could change the font in our MicroPython by simply entering in the command. So here I've entered in the command for the font 28, and let's hit return. So you could see the font immediately displays much larger. And it's more dramatic if we use the Alex Brush font, which is a scripting handwritten font. So let's try that. Okay, we've entered the command for the Alex Brush, and now hit enter. And you see that we're now seeing the Alex Brush font in the screen. In summary, in this video, we demonstrated a working program on a large 800 by 480 display. We explored the Waveshare wiki to understand the components. We discussed the LCD bus modules used to configure the Waveshare components. We reviewed the display and SD card drivers. Hopefully, you learned more about the LCD bus and are thinking of ways to use this new feature. Please comment if you feel other changes are needed. I hope this video helps your MicroPython coding. Thank you for listening.